We're going to talk in this part about nutrient needs for exercise. First, we'll talk about our biological nutrient needs, as exercise imposes additional nutrient demands. Exercise is physical work, so anytime the cell does more work, we have to input more nutrients to compensate. Exercise is more specific than physical activity, which is already included in our total daily energy expenditure equations. Exercise is planned and it's structured, and it's repetitive bodily movement that's typically done to maintain or improve some aspect of physical fitness. And physical fitness can be pertaining to those types related to health, or they can be the types related to sport. There are two major types of exercise. Aerobic types, which are done at lower intensities and require a lower capacity of a person's cell or muscle or any kind of tissue that's being used. The time that aerobic activities are done are typically longer than anaerobic activities, the type that are done at a much higher intensity for a much, much shorter duration because the muscle simply can't tolerate any longer. Aerobic activities, and the main definitive difference between these two exercise types, are that aerobic activities elicit energy systems that require oxygen, and anaerobic activities recruit different types of muscle fibers that can be used without oxygen available. Looking at a spectrum of anaerobic and anaerobic activities, because all activities do fall somewhat on the spectrum, except at the very extreme ends where something like a 1 RM deadlift would take all anaerobic energy, where an endurance or marathon activity, by the time you're up to the number of miles that qualifies for a marathon, you would be relying on 100% of your aerobic energy systems. Looking at the daily nutrient intake guidelines for exercise, we only reference the dietary reference intake, or the DRI, because it is the basis for all nutrient guidelines. This is the largest collection and body of total nutrition research on human beings, and so it's the basis for the professional guidelines, which are mostly published and worked on and commissioned by the American College of Sports Medicine and by obviously universities and institutions that fund research, including the International Society of Sports Nutrition. So these are just two bodies that fund, commission, and invest in, and even partake in research for nutrition for exercise. In the AMDR, we're used to seeing this when we talk about all the nutrients and the range of calories that each of those macronutrients contribute. And for exercise, we see that the AMDR range slightly changes. Instead of having that same distribution, we have a little less fat because the additional calories that are required for exercise should be mainly carbohydrates and protein. And so of those additional calories, 85% are carbs and protein instead of the normal about 70%. So typically fat represents a larger proportion of our total calorie allotment. Nutrient classes for groups. So speaking of carbohydrates and proteins and the nutrients, we could have classified them that way, but I think it made more sense to classify them in the way that we look at why we have nutrition for exercise. What are the outcomes that we're trying to achieve when we plan or strategize food intake for exercise? And it really does boil down to performance. We have goals for performance, and this could be diets that include pre-exercise food, or maybe even foods during exercise to enhance performance, or for recovery. So after exercise is finished, what we need nutrients for to recover optimally. So when we look at the performance elements of exercise and eating for exercise, really we have two different things. Like we mentioned, there's the pre-exercise, or what's called the loading phase. And this is where we're focused on time. Time is the biggest element here because you don't want to eat within 15 minutes of exercise. And you obviously want to eat a little bit less if we're talking about anywhere within a half an hour. Anywhere more than 30 minutes, so anywhere between 30 and 60 minutes, you can have a slightly more calories and slightly more carbohydrates. It's also an important time to make sure that you have fluids, but again, I wouldn't push much before 30 minutes before exercise on having water. Fluids to maintain cell hydration, it's always indicated to have about 1.5 to 2 cups of water about an hour before exercise. The biggest factor in the loading or pre-exercise meal or snack is that it should definitely have carbohydrates that are low to moderate on the glycemic index scale. And of course, we'll go over this when we get to the section on how we process nutrients during exercise. But these low to moderate glycemic carbohydrates ensure that you don't have too big of an insulin response, which would of course affect you during exercise. We also want to point out that both the 1 hour and 30-minute before suggestions for nutrient intake also include limiting our intake of fat and fiber. Fat and fiber both delay stomach emptying and slow the absorption of the carbohydrates. The next exercise performance strategy are mid-exercise nutrients. And mid-exercise nutrients are delivered every 15 to 30 minutes of endurance type exercise. So endurance exercises last more than 90 minutes. And in the cases that you're going to be exercising for more than 90 minutes of, that moderate intensity, long time, then you might want to consider sparing nutrients while you do so. And on a nutrient sparing diet or carbohydrate sparing diet, the important note here, and we'll of course cover these specific foods in the component too, but they're moderate glycemic carbohydrates. We don't want carbohydrates that are too quick in, and we don't want any that are too slow in. So we're looking at moderate glycemic index carbohydrates, and fluids are usually the delivery mechanism of consuming nutrients during exercise, but we really don't need to consume excess fluids unless we're losing lots and lots of sweat. So again, long exercise, hot and humid environments where we're sweating a lot, fluids become important, but otherwise the only reason that we're doing this in endurance exercises is to get those carbs in to spare glycogen. Recovery. So when we're talking about recovery and post-exercise intake, we're talking anywhere between 15 to 60 minutes post-exercise. After that, it just becomes, the regular daily diet. So within 1 hour exercise, it's recommended to consume 2 cups of water for every pound of sweat loss. And then you're like, well, how would I know that? And it's just as simple as weighing yourself before and after exercise to see how much, and then 2 cups of water to replace. Of course, you do need a somewhat sensitive scale for that. So I would just shoot for a cup to 2 and you'll be fine. Excess calories or extra additional calories are typically looking kind of like a meal for the recovery foods. And most importantly, the glycemic index of the carbohydrates should be high. And this is because we want to elicit this very high insulinemic response or a high surge of insulin after exercise because it promotes muscle protein synthesis, which we'll again talk about in the component 3. The most important nutrient alongside those high glycemic carbohydrates are additional protein. We need to make sure protein's adequate for muscle protein synthesis, and this can be done with about 20 to 40 grams after exercise. Now, if you looked at how that played out per the recommendations and compared to what we've looked at so far, we said that the DRI for protein for the healthy adult was 0.8 grams per kilograms per day. So following exercise, a pretty good portion of that daily recommendation should be consumed. If you look at the average man and woman who are 70 and 57 kilograms, it's in that range of about 20 to 40 grams of protein. And again, this is within that first hour after exercise. This is going to make sure that the amino acids that are needed during protein synthesis are available, and so is the insulin. So behavioral nutrient needs for exercise, much simpler topic than times before. Not that there are any behavioral associations with nutrient intake in those pursuing exercise, but really it's honestly boils down to the goals and what the need is for doing the exercise. So we're really just going to look here at, what are the reasons that people are doing the exercise. This might influence their tendency to focus closely on their nutrient intake for exercise. So look, I like this Maslow's hierarchy. If you've ever had a psych class, you've heard of the Maslow's hierarchy of needs. This looks at satisfying needs in this order up to the top. And so if you have rehabilitative needs, you're doing exercise just to maintain your regular daily functional activities. So people who do participate in therapeutic exercise probably aren't as inclined to, load carbohydrates and take those extra measures. Now, this is most of us that participate in exercise. We do it for health related reasons. And, not saying these aren't including aesthetic reasons and mental health, but mostly it's for lowering cholesterol, keeping a healthy body weight, healthy blood sugar, etc. But some of us in the world actually train. And this is a really elite kind of exercise where you're conditioning the cell, you're conditioning yourself, maybe even for some kind of performance, or maybe it's even for just self-actualization. And in fact, if we're talking about a pro athlete that's paid for their exercise performances, then I would probably put those folks down here in the basic needs of why they exercise. But in the case we're talking about the Spartan mud runners and the marathon runners, they're up here in this exercise training and conditioning category. And this is kind of an important conversation because this definitely influences our psychological feelings about our carefulness about nutrient intake for exercise. Looking at the external controls of the human nutrition system, it's the first time we've ever actually been able to bring up the actual external environment of temperature. So hotter temperatures, as we exercise in those temperatures, we dissipate heat through our sweat, which that's how we get rid of our extra heat that we're producing in exercise. And so we lose extra water. So in really hot environments or humid environments where we're sweating more, we may have increased fluid needs. Nutrition marketing does also influence our nutrient intake, and there are certainly products that are marketed specifically to athletes. So we'll look at some of the ingredients that are used in component 2 and some of the, mechanisms in component 3. But here we're just looking at the different types of things that we're told. What are the things that influence what we think and some of the nutrients that we may consume based on what we read on these packages and what we hear in commercials and read in blogs. But you're going to see things like boosts performance, increases endurance, the same things we've said, but enhances recovery. And some of these statements are not necessarily regulated or defined. They're in fact unregulated and undefined as labeled here. This one's a funny one. This is just, again, really getting to the point. I'm not really trying to cover ingredients for performance or mechanisms, but this one's funny because these are the kind of red flags. And if you're paying attention and thinking critically, so the malic acid is supposed to balance the extreme alkalinity. So this product is supposed to help counter the effects of lactic acid. So as the lactic acid accumulates, the alkalinity in this product counterbalances that. So what they're saying here is that the malic acid helps to increase the acidity, right? If you're with me, reducing the alkalinity to help minimize stomach distress. But then how is that going to help with your lactic acid neutralization? So these are, and I wouldn't expect people to know that, but I know you guys understood from maybe high school or elementary the concept of acids and bases. And so yes, I got it. I'm taking a base to help reduce the buildup of acid, but you put an acid in it to reduce the likelihood of the base affecting my stomach. So these are the types of critical thinking glasses that we should be looking through what we're reading on these products. So that's all I have for nutrient needs for exercise. Next time we'll talk about food. We're going to talk in this part about nutrient sources for exercise. We're going to talk first about the nutrients in whole foods. And when we talk about for exercise, just a reminder, we're going to keep hitting on issues related to the timing of food intake. And we're looking for an additional 300 to 500 calories, of which at least 25 grams are carb and at least 20 grams are protein to replace, recover, and to support exercise performance. Now, first, we're going to talk about plants. Plants are naturally pretty low in fat, modest to low in protein, but they have a hugely variable glycemic impact based on their sugar, fiber, and moisture matrix. But before we talk any more about specific plants, let's take a look more about glycemia and the glycemic index. When we talk about the glycemic index of a food, which is familiar to you at this point, we're looking at the response that that particular food elicits on blood sugar. So what your blood sugar does in response to a standard known amount compared to a reference food, which is white bread. Now, glycemic load, first time you've heard this term, is factoring in not only the glycemic index, but also the total load. So the amount of that food consumed. So now it's, less scientific in terms of its comparison to a standard, and it's just looking at the overall impact of total amount of carbs consumed and the glycemic impact of those carbs. And so glycemic load and glycemic index, the difference between those two can be seen when we look at, for example, fruit. So bananas, great choice pre-exercise because even though they have a really high dose of carbohydrates, they also have a high dose of fiber in proportion to sugar. And so it makes their glycemic index lower than, say, watermelon, which is great post-exercise because it has a really high glycemic index. And even though it has way less grams of carbohydrate in total, it has a bigger impact on the response in blood sugar rises. So one thing that to bring out about the load is raisins have a high glycemic load. And this is because they're dense. There's no moisture. And so it's a very concentrated source of carbohydrate. And so it has a modestly high glycemic index, but a pretty high glycemic load because there's no moisture. It's got a lot of carbohydrates per serving of carbohydrates. Hopefully that makes sense to you, but I'm trying to distinguish between load and glycemic index. Vegetables. So in the vegetable group, you would think that potatoes would have a similar glycemic index, but it's truthful that pre-exercise, you should focus on ones with a little bit more fiber to, again, stunt that glycemic effects. So you could have a yam pre-exercise and it would, again, create a lower glycemic impact. Post exercise, you're looking for those higher glycemic impact foods. So you'd go for that higher starchy, regular, like an Idaho baked potato without the skin. That's the starchiest, most highest glycemic way to eat a potato. And again, it has less fiber, so you're going to have that less stunting of glycemic impact. Now, when we look at a regular baked potato, like a regular white potato, if you boil it, it's actually an okay pre-exercise snack or food, whatever you want to say, because the boiling provides, if we were in class, I would survey you, it would be exciting because you would remember when you boil them, it creates that filmy outside texture, which is resistant starch. And that stunts the absorption of the carbohydrates, creating that lower glycemic impact. So again, I'm just really trying to get you to understand that even foods within the same group, some are better for pre-exercise and some are better for post. Same with grains. There's not a huge difference in, the profile of grains, but you could see that how an oatmeal, like an uncooked oatmeal, would have a lower glycemic impact because it has more fiber than, say, a cooked and enriched white rice. And so that higher glycemic impact carb would be better for post-exercise. Now, when it comes to animals, they have a lower glycemic impact overall, but they provide that high protein and high quality protein that we need to recover. And they're pretty highly variable in the amounts of fat. Tuna has essentially none, all the way to beef, which we know has lots. So we'll take a closer look. Meats are always good post-exercise because of that high quality protein. All of those amino acids are in the right doses. Now, protein is probably about the most dense you can get when it comes to like gram per gram, especially obviously you got to drain the can, but we're looking at about 20 grams of protein per can. And also I put up here the fish specifically because fish is also a really good source of creatine. So we'll talk about creatine supplementation in component 3, but fish is a naturally pretty dense source of that. Grilled chicken breast is a really popular post-workout food because it's even higher in protein than tuna, and it has a really nice branched chain amino acid composition. So you can see that these are the branched chain amino acids. Chicken has a really high composition. It has total most, and if you remember, branched chain amino acids are helpful for working out, and well, maybe we haven't talked about it yet, but they're also important for muscle protein synthesis. We touched on it in the protein section. Speaking of high quality branched chain amino acid foods, eggs. Now I know it appears lowest here, but this is just like the best of the best branched chain amino acid sources. But eggs are actually like really high quality in their composition of amino acids too. And they're not very high in protein. So they're good pre-exercise because they're very low in fat and they're providing really high quality protein and low doses of it. So they're just ready and available immediately post-exercise. Milk's okay. It's not the highest in its glycemic impact. So pre-exercise, it makes an okay low protein drink that has a little bit of fluid, but you wouldn't want to drink too much milk, especially whole high fat milk before exercise. It could cause stomach stress. It does, again, like I said, have a lower glycemic impact, but all 12 grams of carbohydrates are carbohydrates. So that's one thing, that it is all at least sugar. There is no fiber to impede its absorption. Post-exercise, a Greek yogurt. So look at double-strain yogurt where it's really high in protein is efficacious, and also those carbohydrates are there. So you're getting the protein that you need and you're getting the insulin-stimulating effects of the carbohydrate. Now, I will say though, just like with the milk, the carbohydrates, the lactose, it isn't that high glycemic index. So that's why it's always best, and we'll talk about this in meals, but to I'm looking at that, to pair yogurt and milk and things like milk with chocolate or yogurt with fruit so that you're increasing the glycemic impact and to contribute to that when you're post-exercise. So some insect-derived products also contribute to pre-exercise foods and ingredients, and especially honey. So we've talked a little bit about honey in the carbohydrate chapter, but 1 tablespoon of honey provides 15 grams of carbohydrate. And it has a lower glycemic impact than sugar or sucrose because it has a nice fructose to glucose ratio. And you probably don't remember this from the carb chapter, but fructose is absorbed with active mechanisms that are a little slower and glucose is a little faster. So if you're looking to stunt that glycemic index a little bit, then you would want to choose honey over regular sugar to sweeten. Looking at processed and formulated foods and meals for exercise, starting with extracts and derivatives. So there are certain sweeteners that are used in sports drinks. Some are derived straight from corn, like for instance, glycerin, where we would take the fat out of corn, we would create a glycerin product, and glycerin is supposed to help with hydration, which we'll talk about later. We also see products like cornstarch. We hydrolyze that cornstarch, or basically, we could call it digest it. That's what our bodies does to it also, to create like syrups, like we've talked about before. But this particular one is called dextrin, and it's commonly used in sports drinks, and it has a nice mid and pre-exercise effect, again, because it has a lower glycemic index than regular sugar. There's lots of functional additives that are also used in products, supplements, and all kinds of, formulated and fortified foods that are purported to have some ergogenic compound. So these are going to be used again in products, supplements, and the things that we'll talk about next. But you see protein, nutrient foods, fats, minerals, vitamins, and all kinds of pharmacologic compounds also: creatine, caffeine, DHEA, carnitine. And again, we'll talk about several of these as we look at mechanisms of exercise in component 3. Looking at packaged products, lots of sports drinks on the market. Everybody is familiar with those, but they're promoted for mid-exercise. The problem with them is, in my opinion anyway, because I have kids that play youth sports, is that they're sometimes promoted for just regular short exercise activities, even 30 minutes of exercise activity. You don't need mid-exercise bottled beverages. They're for endurance exercises, and in those cases, replacing those electrolytes, replacing that fluid, and adding some of those carbohydrates to spare glycogen is a good idea. And of course, like I said, we're all familiar with these products. They're even literally promoted to enhance performance, enhance endurance, and things like that. So we also, though, see post-exercise bottled beverages. And like I mentioned before, chocolate milk is a great post-exercise beverage because it has that nice high protein level and it has that sugar to create that glycemic effect. So whole varieties with more fiber are better for pre-exercise. Post-exercise, it's better to go with the enriched versions that have that higher or elicit that higher glycemic impact. So when it comes to dietary supplements, there are natural and synthetic ingredient mixtures used. Most commonly, you'll see natural things that promote that right on the front. They're like, this is meat, this is the advertisement. It's obviously not exactly real beef, but it's claiming that it's a beef isolate product. We can also see lots of different formats for dietary supplements for sports and exercise. Chocolate, vanilla, and strawberry are common flavors, most likely because those have been shown to mask amino acid flavors. That also kind of relates to down here. You'll sometimes see additives like masking agents that may look like ingredients you're not familiar with, but these are, again, to trick your tongue into not tasting the medicinal and acidic and sometimes bitter astringent tastes of single isolated amino acids. We also see a lot of caffeine and ergogenic stimulants and things like that used in pre-exercise supplements. So pre-exercise or performance supplements and mid-exercise things usually have around 15 to 30 grams of carbs. And they usually, again, come in varieties where they're easy to consume. You can hold them. These are all flat retort packages that, fit easily in a pocket or a fanny pack, or little things that are sweet and pleasing during exercise. In the post-exercise or recovery category, again, I brought up masking agents already, but a lot of these include things to cover those tastes of amino acids, and they're shooting for around 24 grams of protein per serving. Meals for exercise, the most important thing is just making sure that there aren't long periods between meals, because the last thing you want to do, especially if you're bodybuilding, is, have catabolic episodes. So you eat regularly and eat more than 3 meals a day is one way to ensure that there isn't super long periods between feedings. A mix of low-fat plant and animal foods, and making sure that we're paying attention for timing and recovery. So when we talk about breakfast, or not specifically breakfast, but again, it's just kind of reiterating exercise timing. If we're talking about breakfast for a pre-exercise, but in the morning and you're going to work out, if you're exercising on the sooner side within 30 minutes, you're going to keep it lighter. And if you're exercising later, you're going to maybe have the same type of foods, but just a little bit of a larger portion of those. You want to have your nice large portions early in the day and, nice and close to exercise, so that right when your body was about to go all storage on it because of that big meal, you trick it into going into catabolic mode because you started exercising. For lunch, nice, nutritious, nutrient-dense thing like edamame and a sandwich. This would be perfect for post-exercise because you're getting the carbs and you're getting the proteins. For dinner, same kind of concept, but oh, you know what? I just realized I forgot to add baked chicken. But I put the lemonade up here to show you that even if you take a really high protein, healthy dinner, like baked chicken and brown rice, you can just boost that glycemic impact for post-exercise with a nice sugary beverage. So this is the one instance where we're recommending those sugary beverages and juices because they really do drive home that insulin effect that's good post-exercise. For snacks, pre-exercise snacks should again be low to moderate glycemic index. So you're looking for whole grain crackers and a nice high protein legume like hummus. Post-exercise, again, high protein, high carbs. It's again these one instances where we're going, go ahead and pump up the sugars, have the protein bars because they are great to pair with that high protein dose post-exercise. And also same concept, looking at smoothies, using Greek yogurts and sweeteners or fruits. Making smoothies are great post-exercise because of that high protein, high insulinemic effect. If you've noticed, we haven't talked a lot about vitamins and minerals because those naturally come with these nice, healthy whole foods that we're talking about. Vitamin and mineral intake will naturally come with a nicely planned 300 to 500 extra calories that's nicely balanced between carbs and protein. So that's all I have for nutrient sources for exercise. Next, we'll talk about nutrient processing for exercise. Thanks for listening. We're going to talk in this part about nutrient processing for exercise. First, like always, starting with digestion and absorption. And I have to say that it was counterintuitive for me to start with our ordinary order because it would have made more sense to start with muscle contraction and the onset of exercise. And we will start with the onset of exercise, but we'll look at the digestive system first. So right when we sense that we're in an oxygen deficit, we kick in a neurohormonal response that triggers an adrenal response to release epinephrine. The epinephrine causes a constriction of the muscles that line the epithelial lining or endothelial lining of the GI tract, and that's going to restrict blood flow and direct blood flow to the muscles. So right there in the GI system, there's already less blood flow happening, which causes effects in each portion. In the mouth, there's a slight reduction in taste acuity. Usually products designed for mid-exercise are very lightly sweetened. There's a reduced stomach emptying rate, and that's again because blood flow is diverted away. And for some sports like cycling, sometimes there's reflux for pre-exercise meals that are too large or too high in fat. Fat also delays stomach emptying. So then when you position yourself in a manner and the blood is diverted away, it can leave the matter in your stomach for too long and sometimes cause reflux. In the enterocytes, there's an increase in glucose-facilitated electrolyte absorption. And so this always takes place, but during exercise, this is just a mechanism that increases. This is another reason why they use or promote the glucose or sugar in these drinks is because it is needed for electrolyte absorption in a higher way or greater way. In the large intestine, because of the diversion of blood flow, there is a less absorbed nutrients. So you have more unabsorbed nutrients, and because of that, there's more risk of diarrhea or constipation. Nutrient transport and homeostasis for exercise starts in the circulatory system with exercise onset. Like we mentioned, those muscle cells start contracting, and this immediately creates this oxygen deficit. And so the blood is the first place where it is sensed, and immediately there are hormonal responses to recover. So one of the hormonal responses takes place and causes an increase in heart rate. So an increase in heart rate takes place on a very tightly proportionate scale with an increase in ventilation or oxygen uptake. So heart rate and oxygen intake both increase proportionately so that more blood and more oxygen is delivered to working muscles. In the endothelium, there is an increased vasoconstriction in the narrowing in the splenic area, which like we mentioned is the intestines and the liver and in other areas which are less explosively needed at the onset of exercise. And there's an increased relaxation or dilation in the actively contracting muscles, again, to increase blood flow. One of the things that people take as a supplement is caffeine. The caffeine will increase the adrenal response or the epinephrine response that increases heart rate and VO2. Other supplements that people take include omega-3, and sometimes we'll see people take nitric acid. And this is to hopefully dilate better and more efficiently the muscles, and so that oxygen can be delivered more adequately. In the case of nitric acid, interestingly enough, it does cause a slight swelling of the muscle because of an increased dilation. It causes osmotic changes that increase muscle water holding. And so sometimes people take nitric acid because they think they look bigger, or they don't think they look bigger. They probably think they are bigger, but it's just a dilation from the water holding. In the endocrine system, like we said right at the onset of exercise, there is an oxygen deficit. We also know that blood sugar levels drop if we're talking about exercise that continues or sustains. In response to that, there are sympathetic effects that cause endocrine responses that have and cause metabolic changes. For instance, all of these glands are actively increased in their responsiveness, and all of these hormones are increased based on whether we're in the catabolic part of exercise or the post-exercise anabolic part. So we can't really talk here about this one increases for this or that. We'll get to that next when we talk about metabolism. Because for instance, yes, insulin activity increases post-exercise, and glucagon activity is increased during exercise. So all of their activity is increased, and we'll talk specifically next. Oh, and obviously insulin and glucagon are important from the pancreas because they're the most important for sustaining blood sugar, which is the hardest to do during exercise. During exercise, there's also an increase in hormone receptor binding sensitivity. So any hormones that we're talking about involved, there's an increased sensitivity and receptiveness to those hormones at the cell receptor level. When we talk about carbohydrates specifically, there's also, if you guys went back to the carb lecture, you'd remember that for carbohydrates to be absorbed, insulin binds to that cell, and then it triggers this intracellular signaling where GLUT4 is translocated. That GLUT4 comes up, let's just say, for instance, it's not exactly like this, but theoretically, comes up to the surface of the cell membrane, and it activates the absorption of glucose. Hormone-sensitive lipase, or HSL, those are in fat cells, big adipose fat cells. We have lots of fat stored there. Hormone-sensitive lipase breaks down those stored triglyceride. So that activity is increased also. I forgot to say the best part. So people sometimes supplement chromium and vanadium, and these are, micronutrients and that we get in ultra trace amounts in our diets, and they're just present in our diet. We don't need to discuss getting them because we do not misconsume them. But some people take these supplements because they're purported to increase the sensitivity of the receptors to the action of insulin binding. So anyway, there's also increased intracellular signaling, like we said, and this increases because we need more nutrients coming in and out of the cell for nutrient metabolism. So lots going on with increases at the cell level to facilitate or support exercise. Now, the metabolic changes that occur with exercise, again, to keep consistent with our perfect outline and going in the same order, we start with anabolic systems, but it's counterintuitive because this is after exercise. So we're going to start with anabolism to keep it consistent, but after exercise, these are the hormones that are in effect. You've got insulin, you've got growth hormone, cortisol, and based on whether you're a boy or girl, these sex hormones, testosterone and estrogen, and they promote nutrient storage or anabolism. In the nutrient storing tissues like the muscle and the liver cells, lots of glycogenesis going on. Glycogenesis is where we're taking single carbohydrate units and storing those for later as glycogen. So increased glycogenesis in both the muscle and liver. Lots of proliferation in our muscle tissue and other cells also, but lots in the muscle tissue. And we're getting two different kinds of protein synthesis. We're getting structural protein synthesis like muscle fibers, and we're also getting little teeny subcellular compounds, little teeny subcellular proteins like mitochondrial matter, enzymatic matter, hormone production. So we're not only getting that structural protein, we're also getting an increase in globular protein synthesis. And just to be specific, you guys probably remember from chapter 4, but especially in resistance training situations, we're certainly increasing our proportion of actin and myosin, the muscle cells. So in the skeletal muscle, we also, like we mentioned, have a big increase in muscle protein synthesis, but just looking a little bit more specifically at that pathway and why certain supplements are sometimes involved. Testosterone and growth hormone are both present after exercise, and those trigger the mTOR or muscle protein synthesis pathway. Now, sometimes people take the supplement DHEA because it supposedly promotes testosterone production. And sometimes these single amino acids are taken supposedly because they enhance the production of growth hormone. Some, some, I almost said faculty, but some researchers find positive effects, some find nothing. And overall, the results of these things are sort of inconclusive. Growth hormone contributes, and sometimes people do take growth hormone as a supplement too, but growth hormone contributes directly to the production of IGF. And IGF works with insulin to trigger the whole mTOR process. So, obviously insulin and IGF are needed. It's just like what we talked about with cell receptor stuff. The receptor activity kicks it off, and then the muscle protein synthesis happens. We also talked a little bit about leucine in the chapter 4 when we talked about protein. Leucine is the amino acid that on the cell level triggers muscle protein synthesis. And you probably don't remember HMB, but we talked about that in weight loss. It's a ketone. It's a high, like a metabolite of leucine that is also supposed to increase muscle protein synthesis. So I know that was a lot, you guys. All I'm looking for you to understand is that on the, we already talked about muscle protein synthesis, and this is just looking at some of the supplements that you see bodybuilders take, some of the hormones that are involved, and why potentially this might increase your post-exercise recovery. Now, catabolic systems. So during exercise, catabolic systems are dominant. Obviously, we're breaking down nutrients to use them for the expenditures. And involved in that are the hormones glucagon, the adrenal hormones epinephrine and norepinephrine, and then, of course, good old, actually, I don't know what this is right here. I'm not sure what this one is, but it's a protein hormone. I know that. I'm sorry, I forgot that one because I forgot to label it. So obviously, we won't need to know anything about that. The energy systems that are in effect on our metabolic levels. So energy, or ATP, is being regenerated by one of 3 systems. And when we talk essentially, you guys, about why we're even needing to regenerate ATP, we'll talk about this in the functions of all this in component 4, but we're talking about so that muscle cells can contract. Muscle cells need energy to hook and pull in this mechanism that you see happening. So the energy systems that we use to regenerate ATP include 2 that use nutrients, and one is aerobic and the other is anaerobic, but these systems, both glycolytic and aerobic systems, use nutrients to fuel that process, and the byproduct is water. Okay. The system that does not use nutrients, it uses stored phosphinogens, is phosphocreatine system, or the PCR system. Now, we've heard of this system before, but it takes place right at the onset of exercise. It's super high intensity, and it relies on things that are stored in the muscle and that do not rely on oxygen. But this system depletes really quickly, like you can see. And as this system is depleting, you can see other systems are picking up in their contribution to resynthesizing ATP. Now, in our nutrient demanding tissues, of course, in the muscle, we're contracting. So we have those high intensity muscle contractions when we do, like, for instance, sprinting or a rep or jumping. We elicit those high intensity or fast twitch muscle fibers, and they're going to use right away anaerobic systems, both the buffering one, like we just mentioned, the phosphinogen system, which uses locally stored muscle phosphinogens. It uses ATP and PCR because we store some ATP also, and it breaks those down immediately to resynthesize ATP. Now, again, this is right at the onset, but this system depletes very quickly. That's why it's called the buffering system until the other systems can kick in. So some people take creatine supplements because it supposedly increases the amount of creatine that you have in your muscle. But one thing to look at on the shortation notation here of creatine phosphate is that you also have to have that phosphate component. So just because you might increase your muscle content of creatine, if we even do, it doesn't mean that it increases phosphorylated creatine. And even if it does, it doesn't mean that it causes a faster recovery and allows you to do another set faster at a higher intensity. I know I'm talking a lot. I wouldn't expect you to understand the mechanics of creatine, but some people take it. And this is why, because right away at the onset of high intensity things like weightlifting, we rely on the PCR system. Now, if we sustain our muscle contractions, we're going to be using those fast twitch muscle fibers. They're very glycolytic, meaning that they're good at using that stored carbohydrate that's right there in the cell, and they can even do it partially without oxygen. So when we sustain it, like, it's not like the most we can do, but we can do it for maybe 2 minutes. We use these glycolytic systems that break down stored muscle glycogen and break them down to create sometimes lactic acid. So in the case oxygen is not available, we create lactic acid. And for this reason, like we talked about in component 1, sometimes people take buffers because the buffers are supposed to neutralize the buildup of lactic acid, which is supposedly helps you to be able to keep going or push through the endurance or the burning of the exercise. Now, these anaerobic glycolysis systems, glycolysis because we're talking about carbohydrate use, anaerobic because we're talking about, hey, oxygen is not here yet. They use that locally stored carbohydrate and contributes to lactic acid buildup. Now, in the case that we are talking about even longer sustained muscle contraction. So now we're on several minutes into exercise. Now we've started to recruit slower twitch or oxidative muscle fibers, and these have oxidative capacity. So they perform oxidative glycolysis where they break carbohydrates down with oxygen to create not lactic acid, but pyruvate, which like we've talked about before, proceeds on into respiration to, with oxygen, create energy to resynthesize ATP. Now, when exercise continues and we start running a little bit low on what we have stored locally, we can progress into recruiting fatty acids. So fatty acids are recruited, broken down, and sometimes we take stimulants because it purportedly increases our propensity to break down these fatty acids. We break down the fats, we send them into the mitochondria to use them in respiration. And this is the primary or dominant system that we use when we're exercising, at a low intensity for a long time. If you're exercising for 45 or 50 minutes, this system is in full effect past the first, several minutes of exercise. And those other glycolytic and carbohydrate burning systems are, of course, still in use, but, this system takes on to be a bigger portion of total expenditures. Now, people take carnitine because if you remember from the fat section, to get that fat in there, they need the carnitine shuttle, and people think that if they take more of it, they'll be able to have more fat use and hopefully enhance their endurance exercise because of the glycogen sparing effect that it might have. So in a case of really prolonged exercise, we start to have like nutrient, degradation starts happening in these tissues. And so obviously the adipocytes are really kicking into breaking down stored fats, and myocytes or muscle cells and hepatocytes or liver cells are performing what's called gluconeogenesis. And we've talked about this before, but it's where everything's being converted to glucose because at this point, the muscles have used all the glycogen, the liver's almost out of glycogen, and now we're going, the brain is going to need something soon. And so we start kicking into gluconeogenesis where we make glucose to sustain brain activities during really long bouts of exercise. So that is all I have for nutrient processing for exercise. Next, we'll talk about the functions of using nutrients for exercise in component 4. Thanks for listening. We're going to talk in this part about nutrient functions for exercise. So just like with all of the other times we've talked about the nutrient functions, we always start off with structures. So exercise creates additional cell and molecular nutrient structures. So just like we've talked about before, we have these subcellular components, things that are made of proteins and protein matter like mitochondria, cell membrane mass, protein enzymes and hormones, and then all of these little cellular components that are increased when we exercise. Particularly when we do endurance exercise, we have an increase in mitochondrial mass, which of course takes additional dietary protein. Increased mitochondrial mass, looking at the holistic or big picture side of things, creates an increased or enhanced aerobic capacity, meaning that you can do more exercise because you have more little energy engines. Nutrients for exercise also contribute to new tissue structures. So just expanding that out from cellular level, we know that nutrients are needed and are elicited or stimulated from exercise. Resistance exercise causing tears and injuries in those myofibrillar tissues causes myofibrillar synthesis. So increases in nutrient structures from exercise are supported by additional feedings. As you can see in this slide, this was just some data looking at a study looking at the effects of post-exercise muscle protein synthesis with and without feeding. So automatically when we exercise, we have increases in protein synthesis, but when we feed and when we give protein, we see increases in that all the way across to up to 2 days post-exercise. So yes, protein and dietary nutrients and feeding in general increases fibrillar tissue structures, which increases muscular power, or we could also say strength. Nutrient structures for exercise also change the composition of the body in terms of water and electrolyte balance. Glycerol is purported to increase total body water content by changing the osmolarity of the blood, which reduces renal output of fluids. So sometimes glycerol is taken to increase total water, which increases our ability to control our temperature during exercise in hot environments. Electrolyte minerals also slightly change, increasing with good exercise, increasing the demand for these nutrients. And these increased minerals are not only found in bone tissue, but also in fluids. And these electrolytes, which we've heard about lots of times, we associate electrolytes with exercise because of, drinks like Gatorade, but those electrolytes do help us maintain fluid balance in times of exercise and fluid loss, and then replenishing when we have fluid gains. So the electrolyte minerals are also important for body composition. Nutrients and energy for exercise are obviously a huge deal because we can't really exercise without utilizing nutrients. So, of course, nutrients have their functions for exercise because exercise is powered by the energy provided by fat and carbohydrate. And those range anywhere from 4 to 9 calories per gram. Now, exercise time and intensity will dictate which proportion of fat and carbohydrate we're using. So you can see that here, where if we're doing a jog, it's about half carbohydrate, half fat. And so this is called steady state exercise, or about 65% of our VO2 max, or our capacity. Now, when we increase exercise intensity, which just by nature decreases exercise duration or time, we see that there's an increased reliance on carbohydrate, and particularly in the local, the kind that's stored right there in the muscle. The rest of these are pretty unchanged. So exercise intensity greatly changes the proportion of contribution of fat and carbohydrate. Exercise time does also, as we deplete carbohydrates, and fat becomes a bigger supplier of energy for exercise. And this is way out past the 60-minute mark, but really fats do become the predominant fuel source once we exercise for a long time. Now, looking at total energy expenditures, we've seen this several times before, but in the past we've seen resting energy expenditure broken into basal and thermic effect of digestion, and these were a little bit of a larger portion of the total daily energy expenditure. But now, because physical activity, we know we're talking not only about physical activity that is non-exercise activity, like the kind to walk around and do light housework, but we're also talking about exercise, which is, again, that planned, purposeful, repetitive, structured activity. And we might expend anywhere from 400 to 1,000 calories in physical activity, depending on our weight, depending on our lean mass, and depending on what the activity is. So you can see here just a couple examples of calories expended per minute for our average size woman and our average size man. Let's just look at basketball for a man, since it's a nice even unit of 10. This man, 160-pound man, will burn 10 calories per minute playing basketball. And so if he plays for 40 minutes, that's 400 calories. In addition to the 200 of just regular physical activity that we've always talked about every single time, that's a really good energy expenditure. And that's why it takes up a larger proportion of that total bar across the day. Nutrients are also needed for dissipation of thermal heat. So this time we're not talking about nutrients are needed to sustain body temperature. When we exercise, because our cells are doing more work, regenerating more ATP, that creates more heat. So we have to get rid of that heat. And we do that through a mechanism called sweating. And we all know what sweating is. It's annoying and it gets in the way, but it is a very effective thing. And the more in shape you are, the better developed and more numerous your sweat glands are. So sweat is important for maintaining a core body temperature during workout. So obviously our body temperature rises a little bit, but not a lot, which is surprising, and that is maintained through sweat. So sweat rate, to keep up with that in a nice hot environment, requires anywhere from 1 to 2 liters of water per hour. So we're talking a significant amount of water that supports, or that is a function, is to keep our bodies at a nice temperature. We also know that nutrient energy is needed, of course, in exercise for ATP recycling. And we know, when we have ATP and we break that phosphate bond off, it releases energy. And what that kinetic energy is used for is to contract the muscle. And that happens through a series of events where action potential, release of neurotransmitter. That neurotransmitter causes a release of calcium way down into the T-tubule, which is a fine little subcomponent of a muscle fiber. There's the calcium rushing into the cell, and that causes the actin and myosin to bind, pull, And to that effect, you'd be able to see the muscle contract. But I'm just kind of getting to the point of why we need nutrient energy is to recycle ATP, and now more than ever to facilitate muscle contraction. So the functions of nutrients for exercise also include stored nutrient energy. So nutrients are stored in concentrations that are perfect for just daily living, but we can also increase the amount of nutrients that we store with regular exercise and planned diet. So for instance, athletes who carbohydrate load have up to 50% more glycogen stored than people who don't exercise regularly and who aren't paying attention to carbohydrate intake. So having adequate carbohydrate intake is beneficial. It's a beneficial function of diet for exercise because it increases muscle glycogen content, which in effect increases endurance, or enhances endurance as it's sometimes called, by a pretty significant amount. And this is at a pretty high intensity. You can see that it's full capacity. So it increases power. It increases endurance at the highest power that you could. I actually should have put here enhanced endurance and capacity because we're talking about such a high exercise intensity. So carbohydrates and muscle stores of glycogen is important for enhanced endurance and enhanced power in the muscle. Also, this is looking more at not glycogen storage for carbohydrate loading, but when you consume carbohydrates mid-exercise, you actually delay the onset of fatigue. So fatigue is natural. It comes if you exercise long enough naturally. But if you restore by having an intake of mid-exercise carbohydrates, you spare glycogen. And that spared glycogen allows you to use it more locally, sparing what's in your blood and what's coming out of the liver for the brain, which is ultimately what stops us from performing exercise. So delayed fatigue is another function of nutrients for exercise. Another function of nutrients for exercise is enhanced recovery. This is looking at glycogen stores after exercise, post-exercise, up to 3 or 4 days. It's showing low and high carbohydrate diets. So you can see that the higher carbohydrate diets allow for a greater bounce back of muscle glycogen storage. So the more you're engaging in these practices, the more your body acclimates to doing it and enhances your exercise performance. You know, there's a reason that elite athletes are elite athletes. They're obviously skilled and they're born with the right proportion of muscle fibers, and they love their sport and they're passionate about it, and their personality is perfect for athleticism, but it's also because they've conditioned their cells to do these things. Operations for exercise, nutrient operations, so the roles that nutrients play in terms of making sure exercise operates properly. So it involves the catalytic nutrients, as we've discussed before. Nutrients that are needed for electrical activation. We just looked at that little slide a couple seconds back of muscle contraction that requires this influx of calcium. So calcium is an ion and it holds a charge, and its influx changes the electrical potential of that muscle cell. And in doing so, it elicits or allows muscle contraction to happen. So calcium is definitely essential for exercise in its role in muscle contraction. We also know that nutrients are needed for enzymatic action. So we can't do respiration without having these enzymes, right? Enzymes facilitate all these metabolic reactions. And like we've talked about before, the B vitamins are coenzymes in these reactions, particularly NAD and FAD, critical coenzymes in electron transport chain, which is that last step of respiration. We also know that iron is needed because iron is a critical component of hemoglobin, and hemoglobin is what is in our red blood cells that delivers oxygen to our working muscles. So of course, iron deficient diets don't have an adequate amount of iron binding hemoglobin, and they are not as able to or adequate at delivering oxygen to working muscles. So all of the nutrient roles are the exact same as they are in the healthy daily life, only exacerbated for exercise because we have to enhance those stores and we have to enhance our ability to recover from exercise, because really, even though it's good for us, it is a metabolic imposition. That's all I have. Thank you for listening. So we're going to talk in this last component about nutrient status measures for exercise. And here again, we're talking about nutrient imbalances. When we don't have enough, we're malnourished, and there's aberrant or abnormal outcomes because of it. So in the case of excesses or nutrient toxicities, we sometimes can see excess body fat and cholesterol production from too much protein and saturated fat intake. And now these aren't lean proteins. These are when protein is accompanied with saturated fat, like in the case of, beef and really high fat animal meat. These particular problems are particularly exuberant or stand out in populations that really promote meat and protein intake. So like football, rugby teams, sumo wrestlers, that, occasionally some types of sports groom athletes to consume an excess amount of protein and calories. So sometimes nutrients for exercise can cause toxicities. More often, we have deficiencies or inadequate nutrient intake for exercise. And these are usually in the areas of carbohydrates and amino acids, so that we have an inadequate amount of carbohydrate for endurance and an inadequate amount of protein for that new or increased muscle protein synthesis. That usually results in either a limited muscular capacity and or a limitation in cardiorespiratory capacity. And if exercise is long enough, it also contributes to a limitation in neural capacity. So some of the assessments or instruments and measures that we use to determine nutrient status for exercise are our anthropometric measures. Body weight increases and decreases with exercise depending on the type and depending on, where your nutrient status was before. If you had high levels of body fat, weight typically decreases. If you had low levels of lean mass and you're, doing weight resistance, of course, body weight increases. One thing to note is that body mass index, or BMI, is not the best measure to look at when we're talking about exercise, bodybuilding, and athletes, because athletes are systematically a little higher. And if you look at the average weight for a man, anywhere, let's say he's 170 pounds, his BMI is at the most healthy end of the range, even though he's in incredible shape and has a high proportion of lean body mass. So the body mass index measure, which is again a measure of weight for height, wasn't exactly intended to be used in athletics and with exercise. But unfortunately it is used, and it confuses athletes because they think they're overweight when really they're perfect weight. It's just that that's how the BMI works. Circumferences are increased in some areas, like in the biceps, or in the case we're talking legs, maybe in the quads or the hamstrings, the glutes. All of our muscles have the potential to expand so that we can measure them with circumferences and they'll be bigger. We also see areas or circumferences get smaller, like the waist circumference typically goes down with the onset of exercise programs. Body composition definitely changes. If we're looking at the 2-compartment model, it's always as simple as a decrease in fat mass and an increase in lean mass. And that's exactly what we want with athletics or sports and exercise. We don't want to exercise so much that we decrease our lean mass. So we want to make sure we maintain lean mass and increase it and decrease fat mass. Athletes are usually a little bit higher in their proportion. Body composition also is a great status measure, the 2-composition model particularly, for looking at nutrient status for exercise. The more we exercise and do endurance and cardiovascular exercises that are long and elicit the use of fat, we will decrease our fat mass. As long as we do exercises that elicit muscular injury, increase muscle tissue synthesis, we will increase our lean body mass. Sometimes these end up having no effect on total body weight because you have an increase in lean mass and a proportional decrease in fat mass. Now, athletic men and women are typically a little bit lower in their overall percent body fat than regular, just adult healthy men and women who don't regularly exercise. If we looked at the 4-compartment model, in terms of assessments, we could also see changes in muscle and water, increase obviously skeletal muscle mass like we mentioned, but with that an increase in total body water, because muscle cells hold a lot of intracellular water. And so because of that, we would also be able to see changes in a good way in that bioelectrical impedance, which is really a body fat measure, but it's an indirect measure of skeletal muscle mass and intracellular body water. Bone, we also see slight changes in the density of bone with resistance exercise. And as we'll look at in a few moments, it's because of the differences in calcium uptake and excretion. Some of the biochemical measures for exercise status would include urine. If urine is nice and light colored, then you're pretty hydrated. When we exercise a lot and we sweat in high temperature and high humid environments, we do not replace that water adequately. We would have a darker urine color, which would ultimately affect our thermoregulatory capacities and our ability to exercise for a long time in hot environments. We can also measure in the urine nitrogen, and nitrogen is an indicator of protein synthesis. So if we're in a state of a negative nitrogen balance, it means that we're not urinating out nitrogen, meaning those measures go lower, and it's because we're preserving all of that nitrogen we're consuming to build those new tissues. So a negative nitrogen balance is indicative of tissue synthesis, and of course you would see this if someone was on a bodybuilding or a resistance exercise program. Also in the urine, we can measure sodium and calcium. And most likely, especially in the cases of resistance exercise, at least for calcium, we'll see decreases in the urinary levels of these nutrients. And the reason why these minerals decrease in the urine is because we're retaining extra calcium. Resistance exercise increases bone mineral density and it increases that calcium retention, so it reduces the amount of sodium and calcium that we find in the urine. So clinical measures of exercise would include signs, symptoms, and condition of fatigue. So of course, fatigue is a perceptible feeling that sometimes we feel at the very onset of exercise, but in cases of like marathons or like at the end, these are extreme feelings of fatigue. One is called bonking, and it's where blood sugar drops and we're starting to feel a little disoriented. And the other one is called hitting the wall. And it's where glycogen depletion is so significant that the muscle stops contracting. And sometimes you'll see these on best hits or best clips of marathons where people's muscles like freeze up. So these are in severe instances of glycogen and carbohydrate depletion. And again, long exercise. Now, performance measures. Normally we just talk about clinical measures, but in the case of exercise, there are actually performance measures where your coach is standing there going, I'm not sure if carbohydrate loading worked or not. And so in this case, because we're trying to enhance something, your coach can measure, or your personal trainer or your strength and conditioning specialist, stamina, power, distance, speed, accuracy, force, time. And of course, these are sport dependent, exercise dependent. If we're talking about weightlifting, we're talking about a 1 rep max. Did it change if you had a loaded carbohydrate supply? Or how many push-ups could you do? What was your glycolytic capacity? And if we're talking about endurance or the effectiveness of, say, carnitine supplementation, what was your endurance or the time until you were fatigued? So endurance and strength can be measured. And it's certainly a measurement of nutrition status, because we've all had those workouts where we feel on top of the world, and we have those workouts where we feel like we just can't do it. And the difference is your nutrition status. And so those things can be measured, and we do this all the time in how we feel, but they can be measured in the lab or clinical or performance setting also. That's all I have. Thank you for listening.